So the next speaker is Daniel Frisch, if I pronounce it correctly, with deterministic Gaussian sampling with generalized Fibonacci grids. So, Daniel, whenever you want.
Yes. Okay, yeah, thanks for the introduction. We are now talking about Gaussian sampling using the Fibonacci principle. And I'm sure you know the Fibonacci grid already from the sunflower or the daisy flower that you can see here. And you may have heard that it has something to do with the Fibonacci numbers and the golden ratio. And you also may know that when we apply some radial deformation to the points, then the points stay like uniformly or homogeneously, or space. They keep this space filling property, and the plants are also using this because the seeds grow over time when they come from the inside to the outside, and the plant also everywhere has this efficient use of the space due to this property of the Fibonacci points that we can deform the grid along certain directions. What you may not know, that we can also apply this deformation along the tangential direction, and also the points keep their nice and space-filling uniform distribution. Actually, I don't know what to use this for, but for the radial deformation, we can say that we can obtain nice point clouds for any densities that are radially symmetric here. Like, for example, the standard normal density, which is radially symmetric. And now we don't only want the standard normal density, but arbitrary Gaussians, of course. And when we apply the actual linear deformations to compress this circular shape to the ellipsoidal shape, then we see that we are getting here these collisions that you can see, point collisions. The points are clumping up along lines, and we have gaps in between. So this is not anymore doesn't anymore have this nice and space-filling property. And why is this? Because we are only allowed to apply deformations along the radial or the tangential direction, but not horizontal or vertical. But luckily, there is also a Cartesian Fibonacci grid. This also appears in nature when in a cylindrical topology, when you look at the stems of plants and where the leaves are coming out on the sides. And here we are allowed to apply deformations along horizontal and vertical directions. Like, for example, here I imprinted an exponential density along the vertical direction and a sinusoidal density along the horizontal direction. And with this principle, we can get nice samples of every density function that is a joint density of independent marginal densities, because then this joint density is separable into a function of x times a function of y, and then we can easily apply this. And the most important example of these independent densities is again the Gaussian density, which is not only radially symmetric but also independent. And now here we are also allowed to apply subsequent horizontal and vertical deformations. And when we do this, now we can get arbitrary Gaussian densities with a nice space-filling low-discrepancy point sets without any collisions. Okay, let's take one step back and see why we are doing all of this. We have heard it in the first talk of Andrei Straka already. We need this for Gaussian filters, like, for example, the Unscented Kalman Filter you can see on the left here. And it uses very few samples, and therefore the estimation value is often bad, and also the uncertainty, the moment estimations are not very accurate, and this can lead to follow-up errors, because if the uncertainty is estimated in an unconservative way, so it's estimated too low, then this Kalman update step, this balance between the uncertainty from the from the prediction and the measurement gets off balance, and we can have large follow-up errors in the next recursions. And the Unscented Kalman filter has 1 degree of freedom, so you could move the points farther out and introduce some weighting, and for some nonlinearities then it works better. But I think the only way to really improve this is to use more samples simply. And there are some basic methods. You can use samples on the main axis. Before, Andreas Straka was talking about this Gauss-Hermite sampling. I think that there you have equidistant sampling that have weights, but you also can have unweighted samples here. Also there's the so-called randomized unscented Kalman filter, but it also has weighted samples. So if you have weights, you always waste some samples that have low weight and have unnecessary computation power wasted there. I think the main methods to really use any number of samples for your moment estimation in the Gaussian filters is first random sampling. We know this as Monte Carlo simulation, and we also know that random samples always come in clusters and have gaps in other places, so we need we need lots of samples here to get a valid estimate. Therefore, there are the so-called quasi-random sequences that have a more uniform distribution of points, and the space is filled more evenly, and we don't have this, have fewer cases of this close agglomeration of points. So we get the same accuracy with less points. And then finally, there's an optimal way for any density and any number of samples to distribute the samples that are distributed very carefully just according to the density function, and you can get the most accurate result using that number of samples. And that's what we want to dive into more on the next slide, because there are 3 methods available. The first one is the localized cumulative distribution, LCD. There is a distance measure defined between the Gaussian density, the continuous Gaussian on the one hand side, and the Dirac mixture on the other side. And this distance measure is then minimized via gradient-based optimization. And the unknown parameters that have to be optimized are all the sample locations, and of course it is computationally pretty expensive, especially if you have many samples. Then the second method is the projected cumulative distribution, PCD. This method is more like an expectation maximization. It's gradient-free, and therefore the whole estimation process, the whole optimization process is easier and better to calculate, but it's still an optimization process, and you need a few iterations to come up with a nice point distribution here. And now finally we are coming to the new proposed method, the Fibonacci method, where you can obtain these samples here without any optimization you have to do. And this is also what this talk is about. When we look in the literature about Fibonacci grids, we read that in the case of more than 2 dimensions, no recipe other than trial and error is known for finding good lattice points. In any case, explicit constructions analogous to the Fibonacci lattice are not known in higher dimensions. This lattice rule has proven optimal discrepancy in 2 dimensions only. Fibonacci lattices in 2 dimensions have a certain optimality property, but there is no obvious generalization to higher dimensions that retains the optimality property. So the common understanding seems to be Fibonacci grids exist only for 2 dimensions, but James Purser noted that a system of number of dimensions minus 1 mutually commuting and multiplicatively independent integer component symmetric matrices with shared eigenvectors aligned obliquely to their basic Cartesian directions guarantees the existence of an associated Fibonacci type grid. So here we have grids that have this Fibonacci property that we are allowed to deform them along certain directions in dimensions other than 2 as well. And the most basic way to explain this generalization is like this. When you look at this small dynamical system, when we give it the initial value 1, 1, then it produces the Fibonacci numbers, because this upper line in the system matrix here just adds the last 2 numbers, and the second line here stores the previous value. And if we apply this equation here iteratively, then all the Fibonacci numbers come out. And when we look at this matrix, we see some kind of pattern, and that we can extend to 3 dimensions like this. Now there's more theory behind this, as you can imagine, but for our purpose here, this is enough. If you know these are the Fibonacci matrix, this is the Fibonacci matrix in 2 dimensions, and this is a generalized Fibonacci matrix. And later we will need the eigenvectors of this matrix. Now here's an overview what our method does provide. So you give it your wanted number of samples and the dimension you're in and the covariance matrix you need. And then we do this proposed deterministic sampling based on the Fibonacci grid, and out comes, and it returns you these sample locations. For the notation, we say L is the number of samples, 100 in this example, D is the dimension, and then we have the covariance matrix. In this example, we have standard deviation 1 and 0.3 along the main axis here, and also a rotational part of 30 degrees. And the resulting points are x1, x2 collected into this matrix, and that contains all this, the coordinates of all these point locations. Now this was a 2-dimensional example. We can also do it in 3 dimensions. Then we have 3x3 covariance matrix and also 3-dimensional point coordinates, where the visualization here is of course a 2-dimensional projection of these points. Now how does the construction of the points actually work? So we start off with regular grid, just this regular grid as we know it, and then we rotate this regular grid, where the rotation matrix is the matrix that contains the eigenvectors from the Fibonacci matrix that we saw before. And then we just remove the outer points here until we have a square or a cube in 3 dimensions or a hypercube in higher dimensions of uniform grid points. Then we have already the uniform distribution. And by the way, in the lower part here, you can see just for visualization what would happen, how it would look like if we applied a vertical deformation to 20% here. So for the regular grid, of course, all the points would clump together or get close to each other along these lines and with gaps in between. But if we do instead the deformation along the directions that are defined by the eigenvectors of the Fibonacci matrix, then we keep a really homogeneous distribution of points here. Of course, the points are closer together than here because we have the same number of points in a smaller volume, but they have the same distance to all their neighbors. Okay, now when we have the uniform distribution, how do we get to the Gaussian? Simply by introducing the inverse transform. So we take the density function of the Gaussian, of the 1-dimensional Gaussian, and its cumulative, and then the inverse of the cumulative, and apply this to the x-coordinates. Then we obtain to this here on the left side. And then we do the same thing to the y-coordinates, inverse transform. Then we have the standard normal Gaussian density. And then we apply vertical or horizontal deformation so that we have the correct ratio of eigenvalues of the covariance matrix here. And finally, we apply the rotational part of the wanted covariance matrix, and then we have our arbitrary Gaussian perfectly sampled. Here's a small animation where you can see how it works when I modify the x-coordinates or the y-coordinates. And it's very interesting to see how it happens that the points keep their uniform distance to each other. So this, we heard this keynote this morning, interesting, and it was about parallelization. So this would also be perfectly parallelizable because I just have to change the x-coordinate of each component or the y-coordinate, and normally when I want to do something like this, I always need to check the current neighboring points and keep the distance to the neighboring points as big as possible. But here, due to the properties of the Fibonacci grid, and when I do this deformation along the right axis, then we keep this nice arrangement of points just by, we don't have to check the neighbors for this. Now finally we have a small evaluation. So I take a three-dimensional random vector with zero mean and the covariance with 5, 1, 0 as eigenvalues and some random rotational part. And then I take some nonlinear function. Here this is the L2 norm of this three-dimensional vector. Then I get this value y. And then I estimate this value y based on different samplings of x. And here we see the result. So the dashed black line is the ground truth, and the red area shows the range of the results when I use random sampling. I think I used 200 rounds of random samples here and showed simply the range of results you can get there. The purple one shows the range of results for the LCD method, and the green one shows the results for the proposed Fibonacci method. Now when we subtract the estimated value from the ground truth, we get to the more well-used root mean square error formulation or visualization. Here we can also see that the proposed Fibonacci grid in green is comparable or even better than the state-of-the-art sampling methods. Okay, concluding, we have achieved an optimal deterministic sampling for both uniform and Gaussian distribution that needs no numerical optimization for the first time, and it works in dimensions 2, 3, 5 and also 6, 8, 9, a bit slower. Yeah, and future work includes that we apply this to more density types than just uniform and Gaussian, and to use lattice rules and Kronecker sequence to apply the uniform Fibonacci grid. Then it works also in higher dimensions and on periodic manifolds. Yeah, thank you very much for listening. I hope it was interesting, and if you have questions, please ask.
Thank you, Daniel. It was very interesting. So we straightforward, we have a question from Andre.
Yeah, thank you, Daniel. That was very interesting. My question is, have you considered comparing all those sets or rules with the density itself by means of some distance, like Kullback-Leibler divergence or so, in order to find a criterion according to which those different sampling methods can be ordered?
Yeah, that's a good question. I mean, when you have such a distance measure, you already have a method to obtain the samples, as we did with this localized cumulative distribution in past years, where when you have a distance measure, it also defines a distance measure between Dirac mixture and Gaussian sampling, and then you can minimize it and use this for sampling. I think for Kullback-Leibler, I don't think because the thing is most distance measures you can't use for to compare continuous densities with Dirac mixture, because Dirac mixture they are on continuous domain, but only have a compact have only single points as support. And if you use the Kullback-Leibler, you have the logarithm of the density and divide it. If you use Dirac mixture there, I don't think this would work as a distance measure. Therefore, I simply used some example. Of course, this is just an example, and doesn't get the general. There may be other functions where it's different. I was also thinking about using some Fourier transform in a journal version of this that would cover more types of functions, more types of nonlinear functions. Get some average over many functions that would be possible here.
Yeah, thank you. I know that the Kullback-Leibler could not be used in this case because it's used or it's usable mostly for two continuous densities. But the idea was this is somehow an indirect indicator of the quality. So the question was rather if you considered finding and some direct assessment of the quality by comparing a distribution or PDF with the point-based approximation.
Yeah, the localized cumulative distribution attempts to do this because it uses, you can think of it as a kernel. So you put a kernel over the Dirac mixture, and then you have a continuous distribution, and then you can compare it to the continuous Gaussian. But of course, it depends on the kernel size, but the localized cumulative distribution does vary the kernel size and also integrate or average over all possible kernel sizes up to infinity, and that's how you get a good result, good measure to compare densities. And as you see on the left here, what comes out if you minimize this distance measure looks very good. Another way is the projected cumulative distribution. Here we calculate the one-dimensional projections along all directions, so basically the Radon transform, and then also we have a continuous measure where we can always compare the one-dimensional the one-dimensional cumulatives. That we have step functions for the Dirac mixture and the continuous cumulative Gaussian, and that we can also compare easily.
Yeah, thank you.
Okay, another question from the audience, maybe? So, in your perspective, you said that you want to explore these other kind of techniques and other distributions, and it's surprising that you don't say that you will apply this to filtering.
So yeah, of course, yeah. This is what we intend to use it for filtering. I mean, it can be used as a drop-in replacement in the Unscented Kalman Filter. Yeah, right.
Yeah,
that's right.
That you can apply it to anything. Even you can apply it to Fibonacci importance Gaussian filter with Andre. So you can apply this to anything. Yeah. And so, and which is compared to the number. So on these Gaussian sampling rules, so like the quadrature and the cubature, that they ensure a number with a given number of points, the accuracy of the nonlinearity that you approximate correctly. So which are the number of points that you must select with your rule? So I don't know, for the cubatures you have 2 times the number of the size of the state, or for the quadrature, alpha to the power of the dimension of the state. So here you select the number of points that you want, or you have any way to set an accuracy of the result with respect to the number of points, or I mean,
because for the Monte Carlo simulation, you have some guarantee, right? You have some. I mean, yeah, the more samples you use, the better the result is, obviously. But right, for the Monte Carlo, you always have this guarantee that the accuracy for Monte Carlo result is on the order of 1 by square root of the number of samples, and for the quasi-random sequences, you have this here logarithm of number of samples to the power of the dimension you're in divided by number of samples. And this, yeah, we haven't looked into the discrepancy of this method and so on. That there's a huge literature on this quasi-random stuff, and it's very mathematical. But I think it should be slightly better than these quasi-random sampling methods. And these are for uniform densities. And if we have this case where we have the Gaussian sampling, then it's an interesting direction to look into. If you could have some quality measure like this, it's probably possible somehow.
Yeah, that would be a good point too. Okay, thank you very much. I think that we have to move to the next one.
Mm-hmm.
Thank you very much, Daniel.
Yes.
Very interesting.